The script opens inside an invisible geometric illusion, where distance is measured not in meters, nor kilometers, nor even light years, but in an angle projected across the trembling sky. A measure that does not describe how far something is, yet reveals its distance. A number that means nothing until the cosmos triangulates itself around it. A cosmic riddle born not from movement, but from stillness. The narrator reveals the strange paradox. The parsec is not a unit of distance because of distance. It is a unit of distance defined by how something appears smaller. An astronomical illusion, rooted in the shift of Earth's orbit around the Sun. A distance that expands as Earth moves. A measurement based not on what we see, but on how what we see appears to shift. Space is revealed not as emptiness, but as parallax, distortion, and cosmic geometry. The viewer is pulled into the central mystery. How can distance be defined by a shape that never exists in reality? Why does the universe reveal itself through angles rather than size? Why did astronomers invent something that makes no intuitive sense, yet underlies everything we know about stars, exoplanets, and the structure of the Milky Way? Fade into darkness, only the drifting constellation of Centaurus remains. In the earliest nights of recorded thought, the sky was a ceiling of perfection. Stars did not drift, did not swell, did not fade. They did not reveal scars of origin nor hints of motion. They simply existed, like crystalline points embedded into a flawless dome. Ancient astronomers stared upward with sharpened reeds, counting, naming, mapping, but unable to answer the one question that carried the weight of every civilization. How far away are the stars? Distance in the heavens could not be grasped, because nothing in the sky shifted. The moon moved, the sun migrated across its daily arc, even wandering planets slid through constellations. But the stars, the true stars, remained still. To the ancient mind, that stillness meant something very simple. If a body does not move, then either it sits infinitely far away, or it sits attached to a shell that rotates around Earth. This illusion lasted thousands of years. From Sumerian tablets to Egyptian astronomical ceilings, stars were recorded with extraordinary detail, but always as patterns, not as objects occupying measurable space. The brightest constellations, Orion, Draco, Lyra, were recognized not as distances but as symbols. Their positions in the heavens carried seasonal meaning, ritual significance, whispered cosmology. Yet no scholar, no priest, no mathematician could define their remoteness. The human mind was prepared to measure land, to divide kingdoms, to trace the curvature of rivers. But the sky remained unreachable. The Greeks changed that. One philosopher in particular proposed something radical, Aristarchus of Samos. He was among the first to suggest that the Earth was not central, that it circled the sun. And if Earth moved, then stars must appear to shift relative to one another over time. A subtle wobble. An arc drawn by presence. A displacement so small that the human eye would never see it. That displacement would later be called parallax. Aristarchus brought forward a thought that fractured the perfection of the heavens. If stars belonged not to a frozen celestial shell but to independent locations, some nearer, some infinitely farther, then distance could be measured through angular motion. If Earth traveled from one side of the sun to the other, the vantage point changed. The geometry changed. The angle to a distant star changed. A triangle was formed between two vantage points on Earth's orbit and a single star. And that triangle could reveal the distance to the sky. It was revolutionary and impossible, because nothing moved. No matter how long ancient astronomers observed, no star shifted against another. Constellations retained shape not just season after season, but generation after generation. Orion's belt remained identical to drawings carved centuries earlier. The Pleiades remained a frozen cluster. Even Sirius, the brightest star visible, did not drift. And because nothing shifted, Aristarchus was dismissed. The heavens were declared infinite, unreachable not in thought, but in mathematics. Greek geometry could calculate the angle, but only if it existed. It did not. And because the angle was absent, astronomers concluded the heavens must be immeasurably vast, larger than any instrument could conceive. Starlight carried no size information, no indication of depth. Stars looked identical on the surface of the dome. Their brightness varied, but brightness carried no meaning, because distance was unknown. A faint star could be near or unimaginably far. A bright star could be enormous beyond scale, or small yet close enough to appear bright. Light had no map. Civilizations accepted that the cosmos did not reveal distance. The Babylonians tracked eclipses, built celestial tables broken only by natural catastrophes. The Greeks drew geometric diagrams of planetary motion. The Chinese chronicled nova explosions. The Islamic Golden Age refined astronomical instruments to angles thinner than a whisper. But still, no star shifted. Every culture, no matter how advanced, reached the same wall. The heavens looked like infinity. If the stars were infinitely distant, then Earth was truly central. Not spiritually, not symbolically, but geometrically. A motionless sky meant Earth was fixed in privileged space. Thus emerged cosmologies that crowned humanity with cosmic symmetry. Distance, therefore, was forbidden knowledge. Only philosophers attempted to breach it. Observers lacked mathematical precision, and telescopes did not yet exist. Even with instinctive reasoning, they knew something remained unsolvable. If stars lay infinitely far away, distance was not something that could ever be measured, not to a single one. Yet the truth was something stranger. The stars were not infinitely distant. They were close enough that the entire celestial vault should have warped when Earth moved. But the shift was smaller than detection could allow. To detect motion, the angular displacement between stars must exceed what the eye can resolve. Human vision, at its limit, detects about 1 arcminute of angular separation. But Earth's shift, even over millions of kilometers, introduces movement of thousands of that. The ancient sky offered no detectable motion, not because it lacked motion, but because the cosmos dwarfed the tools available. It was a paradox of scales. Earth traveled through space. Yet no measurable consequence appeared in the heavens. Even when philosophers whispered of galactic depth, the stars remained a single continuous surface. The first hint of the truth did not come from astronomy at all, but from geometry. Euclid taught that perspective defines size. When an object moves farther away, its perceived angle shrinks. The same rule applied to stars, but there was no measurable shrinkage, no separation. Therefore, the stars must be so far away that Earth's motion causes no change. This idea haunted the ancient world. If the stars appear fixed, then they must be impossible to reach. And distance itself must be infinite. That thought dissolved ambition. For over 1,000 years, distance was abandoned. Astronomy became prediction, not measurement. The positions of stars mattered not because of their remoteness, but because of their recurrence. What mattered was that Sirius rose near midwinter, that Arcturus marked the agricultural cycle, that Orion sank when harvest waned. Distance had no purpose. Until mathematics quietly matured. The medieval era introduced lenses, but still no shift. Renaissance optics refined measurement, but still no change. Earth moved around the sun, as Copernicus later declared, and as Galileo confirmed through the moons of Jupiter. The Earth was finally proven to be in motion, but even then no star betrayed its distance. Reality, thus, separated into layers. Stars stayed still. The sky possessed a structure that could not be decoded. Distance in astronomy could not yet be imagined. But the moment motion became real, truly real, distance was destined to follow. Because if Earth revolves, then perspective must eventually separate. And if it separates, even by the smallest measurable fraction of angle, then a triangle emerges between Earth, its former location, and a star that stands beyond. That triangle, when solved, would rupture the infinite ceiling. Eventually, this would happen. Eventually, the sky would shift. But in this early age, stars continued to disguise reality behind stillness. The cosmos remained immeasurable. The night sky remained silent. And the most fundamental distance in astronomy, the distance to a single star, remained unknowable. The mystery of remoteness did not begin with measurement. It began with the absence of motion. A universe visible, brilliant, vibrant, yet intangible. The first astronomical puzzle was not how far the stars were, but why they refused to reveal that they were far at all. For thousands of years humanity lived beneath a quiet deception. The stars were not fixed. They only waited until the moment precision arrived, until the moment motion could finally be seen. And when that moment came, the heavens would rupture into measurable space, and the idea of distance would cease to be philosophical, becoming instead a number that unlocked the universe. For centuries after Aristarchus first whispered the possibility of a shifting sky, humanity continued to look upward and find nothing changed. The stars, even through the first crude lenses, remained flawless points of light against a background that never rippled. The constellations held the memory of civilizations that no longer existed, and their shapes were so perfectly preserved that ancient drawings matched the sky of later eras almost indistinguishably. The refusal of the stars to move became more than an observational absence. It became doctrine. Philosophy, theology, mathematics, each in its age, absorbed that stillness as truth. For if the heavens were perfect, it was because they were placed beyond earthly imperfection. Because movement implied distance, and distance implied relativity, the absence of movement became evidence of divine geometry. In medieval universities, in Islamic astronomical texts, in Renaissance academies, the sky was referenced with an implicit certainty. The stars do not shift. Therefore the heavens are bounded. Therefore Earth is central. That logic remained stable because nothing contradicted it. The telescope, when it finally emerged, was expected to expose the deception, if deception existed. When Galileo raised his instrument toward the moon, it betrayed craters, valleys, and fractured light. When he turned it toward Jupiter, it revealed moons that orbited another world. But when he looked at the stars, and he looked deeply, their stillness survived. The telescope expanded human sight, yet distances did not unfold. The sky did not tremble. The constellations rested exactly where ancient scholars said they would. Even when recorded night after night, season after season, no star slid against another. Discovery became disappointment. Modern historians read accounts of early astronomers describing something close to intellectual dissonance. The Earth was now mathematically suspected to be moving through space, yet nothing in the heavens responded. If Earth orbited the Sun, geometry demanded a shift. If the vantage point of observation changed, angles must also change. But in practice, they did not. From cathedrals to observatories, that absence was defended as perfection. The concept of a celestial sphere, smooth, flawless, motionless, endured. The Earth occupied the center not because it was proven to be central, but because nothing revealed otherwise. What emerged was not simply astronomy, but cosmological certainty. Humanity, and therefore Earth, held privileged place. To challenge this arrangement was not merely to challenge science, it was to challenge worldview. Parallax became dangerous. Not because it existed, but because its discovery would unravel symmetry. For centuries, the mere idea of measuring parallax raised philosophical tension. If even one star shifted, even a fraction of a measurable angle, Earth would be displaced. Human location in the cosmos would no longer be special nor geometrically unique. The sky would gain depth, and depth implied smallness. In this era, scientific failure sustained identity. But beneath that failure, quiet suspicion accumulated. Johannes Kepler worked with the precision of geometry, refining planetary motion, deciphering orbits, and insisting that starlight must reveal perspective if one had tools sharp enough. He predicted parallax without ever seeing it. His calculations suggested that stars lay farther than any instrument could reach. That distance implied enormous scales, distances so vast that the sky became an ocean of invisible depth. Kepler did not claim proof. He claimed inevitability. Years later, Isaac Newton followed this quiet trail. His theory of universal gravitation demanded physical distances, demanded measurable separation. If gravity acted between bodies universally, then stars could not sit on a single dome. They required space to exist in. They required distance. Newton believed parallax must be detectable one day. Not because it had been observed, but because the universe forced it to exist. Yet even Newton, with his instruments and theoretical certainty, saw nothing. The sky retained its illusion. Astronomers began recording stillness with increasing precision. The more closely they measured the heavens, the more they confirmed absence. It was not merely that stars did not shift. It was that stars remained so deeply fixed that the motion of Earth, the motion Galileo had proven through planetary alignment, seemed unable to imprint itself into the background of starlight. Scientists kept waiting for the moment when motion would reveal itself. Nothing arrived. The more telescopes expanded, the more motion withdrew. While Earth completed orbit after orbit, stars retained mathematical denial. Ancient star charts not only aligned with contemporary measurements, they aligned to the accuracy of fractions of degrees. The farther the instruments reached, the more infinite the surrounding space appeared. What began as philosophical acceptance became scientific validation. The sky does not move. It is vast enough that nothing reveals depth. Distance is immeasurable. This illusion endured because the universe was larger than imagination, and because instruments lagged centuries behind theory. Religious cosmologies strengthened under this absence. Philosophers argued that heavenly perfection was intentional, that stillness proved purpose rather than impossibility. The ethereal sphere became a boundary between the region of change and the realm of permanence. Earth belonged to the domain of time. The stars belonged to eternity. That dichotomy shaped civilizations. Across empires, the unmoving sky became a narrative, a declaration that humans lived under a structure that could not decay. It reinforced the idea that meaning existed above, not below. And because nothing contradicted this belief, nothing challenged it. Even when Copernicus placed the sun at the center. Even when Galileo revealed planetary motion. Even when Kepler charted elliptical orbits. The stars remained immune to consequence. In this era, Europe feared parallax, not scientifically but culturally. It threatened alignment. It suggested demotion. The absence of parallax preserved familiar order. But beneath history, the truth remained unchanged. The sky moved, only more faintly than humanity could see. A single star's parallax shift was microscopic, less than 1 arcsecond for most visible stars. Human eyes resolve 60 arcseconds. Early telescopes resolved slightly better, but not enough. A shift existed, but drowned beneath resolution. The absence of measurement was never absence of motion. This was the frozen universe, not because the universe lacked motion, but because motion lived at scales humans could not yet penetrate. Generations passed not waiting for discovery, but living under misinterpretation. Astronomers continued mapping stars, and their inability to detect movement reinforced earlier assumptions. Constancy created confirmation. The deeper consequence was subtle. Because nothing displayed depth, astronomy stopped searching for distance. It measured positions, not remoteness. It observed brightness, not magnitude. The distances between stars remained unsolved because they remained unprovable. Parallax became a phantom idea. Ignored not because it was disproven, but because it refused to emerge. Yet beyond this silence, thinkers like Newton and Halley whispered its eventual arrival. If instruments sharpened, if Earth-based measurement improved, the sky would fracture into motion. Halley himself suspected that constellations would one day shift, even predicting eventual alteration in star patterns. He wrote of transformations so slow that it would escape lifetimes, but not eternity. It was the prediction of movement without its observation. This era held contradiction. A moving Earth in a motionless sky. A physical universe that denied physical consequence. Mathematics predicting depth without being able to reveal it. It was a scientific paradox. Distance existed, but invisibly. Depth existed, but mathematically, not observationally. Until measurement sharpened, the cosmos could not reveal its structure. And so the sky remained frozen, not as truth, but as limitation. Another generation would pass before precision would finally exceed nature's subtlety. A telescope, finely engineered, placed in the right location, operating with extraordinary stability, would reveal the slightest of stellar displacements. And that displacement, that impossible angle, would break thousands of years of illusion. But in this era, before that moment arrived, humanity occupied a unique intellectual boundary, knowing the universe must be three-dimensional, while watching it behave as if it were not. A universe without depth. A sky without relative motion. Distance without evidence. Only when observation evolved beyond what the human eye could perceive would the stars finally shift, and the ancient dome would collapse into measurable space. For thousands of years, the sky had remained silent. The constellations had held their patterns so perfectly that human memory became indistinguishable from celestial permanence. But then came a night, one that would exist not because the stars changed, but because humanity finally developed the patience to see what was always there. The year was 1838. In a quiet observatory chamber in Königsberg, Friedrich Wilhelm Bessel waited for motion so impossibly small that most of his contemporaries believed it did not exist. His target was not a bright star, nor one considered cosmically important. It was 61 Cygni, faint, unremarkable, invisible to the naked eye in urban skies even today. It had been catalogued centuries earlier, but nothing about it suggested significance. Except one thing. Its subtle drift across the sky, recorded slowly over decades, hinted that it might be closer than other stars. Bessel understood that if the Earth truly orbited the Sun, then stars could not remain fixed. They had to shift, subtly, rhythmically, like objects seen from alternating perspectives. The ancient failure to see this shift was not because it did not exist, but because its scale was beneath the threshold of human ability. Bessel constructed the finest micrometers available at the time, precise enough to measure angles smaller than anything previously recorded. His process was brutally slow. Each night, the position of 61 Cygni was measured not once, but many times, against a carefully chosen reference star. The displacement would be smaller than a grain of sand seen at kilometers of distance, smaller than the width of a single hair viewed at the far end of a cathedral nave. But Bessel believed it would reveal the depth of the universe. He waited months. He repeated measurements. He corrected atmospheric distortion. He recalibrated the micrometer lenses. And then it happened. The star shifted. Not permanently. Not continuously. But cyclically. Over 6 months, as Earth moved along its orbit, 61 Cygni tilted against the background sky. When Earth returned to the opposite end of its orbital ellipse, the star returned to its original position. It was the celestial equivalent of perspective in motion, the universe responding to geometry. For the first time in human history, distance was not a guess. It was a number. Bessel published the result. 61 Cygni was 10.4 light-years away. Earlier records list it as 3.526 stellar units before light-year terminology existed. The shift he measured was only 0.314 arcseconds, less than 1/3000th of a degree. It was smaller than what ancient astronomers believed measurable. Yet it was real. That fraction of a degree shattered the static universe. The stars moved. The heavens were not fixed. Depth existed. And now it could be measured. The ancient dome eroded. The celestial sphere dissolved. For the first time, humanity understood that the sky was three-dimensional. What Bessel had measured was what astronomers had feared, predicted, rejected, and philosophically resisted for nearly 2,000 years: stellar parallax. But hidden beneath this triumph was something larger, a mathematical revelation that would redefine cosmic measurement. Because with parallax came geometry. Imagine a triangle. One point on the Earth in January. One on Earth in July. The final point on a distant star. Two identical points separated by the diameter of Earth's orbit, about 300 million kilometers. A line drawn between those two observing points formed the base. The star formed the apex, creating a triangle so narrow that its angle was nearly imperceptible. But inside that angle lived the universe. Bessel did not just prove that the sky shifted. He proved that distance could be extracted from movement. If a star shifted by 1 arcsecond, just one, the length of that triangle's sides could be calculated. And that ratio defines something new. A universal unit. A distance born not from the size of the Earth, but from the motion of Earth through space. This would become the parsec. A single parsec is defined by a single measurement. When a star displays parallax shift of exactly 1 arcsecond over half an orbit. Meaning, when Earth moves 149.6 million kilometers from one side of its orbit to the opposite, and that shift causes a star to change its apparent position by 1 arcsecond, its distance is 1 parsec. The number that results is astonishing. 1 parsec equals 3.086 times 10 superscript 1 superscript 3 kilometers, is almost equal to 3.26 light years. It is a distance extracted not by stretching a ruler across the cosmos, but by letting space reveal its own structure. With one measurement, humanity learned. The universe is not immeasurable. It is calculable, precise, obedient to geometry. 61 Cygni was no longer just a point of light. It became a landmark, an anchor in the fabric of cosmic depth. The discovery did not merely give distance to one star. It opened a mathematical gateway. Suddenly everything else could be scaled. Stars farther away than 61 Cygni exhibited smaller shifts. Stars beyond parallax resolution hinted at distances spanning tens, hundreds, even thousands of light years. The silent night sky unfolded into tiers. First nearest stars, then clusters, then the faint wash of the Milky Way, then other galaxies, then quasars, and eventually cosmic microwave background radiation, light older than stars themselves. All of this could be layered into numeric depth because of one faint star and one angle smaller than thought measurable. The universe now possessed ratios. A distance in space was no longer metaphorical. It had units. It could be whispered in laboratories. It could be transmitted to observatories in distant continents. Parsec became the unit that calibration revolved around. Telescopes could now be compared. Parallax tables emerged. Distances were archived. What was once infinite became measurable. What was once sacred became mathematical. Even today, the geometry remains exact. Earth at one side of its orbit, Earth at the other, the star above, 2 lines, triangle, and the angle between them, less than a degree, measured in arcseconds. And through that angle, entire galaxies have been scaled. Bessel's moment was microscopic in motion, colossal in implication. It broke the last philosophical shield separating humanity from cosmic honesty. The static universe died in 1838. In its place emerged depth, motion, perspective. The universe acquired shape. Distances that would one day guide space missions, model galactic expansion, and quantify the reach of gravitational waves were born through a single measurement of a dim star hidden between Cygnus and Lyra. That night the stars finally shifted, and the cosmos became real. There is a distance in astronomy that seems to exist only because Earth refuses to stand still. It is called the parsec, an attempt to measure the immeasurable, defined not by an object's size, nor by anything physically marked in space, but by a position Earth once held, half a year ago, in its wandering orbit around the Sun. A fragment of distance carved into the moving geometry of motion. To understand it is to accept a strange truth. Distance in astronomy is not stationary. It is relational, fluid, determined by how a world moves through the void. For centuries, humans assumed distance must be something fixed, something that could be pointed to, charted and labeled. A field could be paced across. A sea could be crossed with ropes measuring knots. A kingdom could be mapped edge to edge. But when the question turned toward the stars, distance dissolved into something abstract, something that could not be walked, reached, or physically touched. The cosmos offered no measuring rod, no fixed post to triangulate against. And so astronomers built one out of motion. Earth orbits the Sun. That orbit forms a path. That path becomes a baseline. Every 6 months, Earth stands on opposite sides of that path, like a traveler returning to the far end of a cosmic bridge. That shift, roughly 300 million kilometers from position to position, creates a triangle. One vertex is a star. One is Earth now. One is Earth half a year ago. And that triangle defines the parsec. It is not measured in meters, not traced in any physical sense. It is inferred by angle. A small angle, so small that early telescopes could not detect it, became the key. If a star shifts in Earth's sky by a single arcsecond when Earth has moved from one side of its orbit to the other, that star sits 1 parsec away. A distance not defined by its own nature, but by the mobility of an orbiting planet. This is what makes the parsec counterintuitive. It cannot be drawn on paper without motion. It cannot exist without remembering where Earth used to be. A distance defined backward in time. It means that astronomy turns the universe into a geometry of memory. To measure a star, one must recall where Earth had once stood 6 months before. This is unlike any measurement humanity had known. When an architect designs a structure, every segment exists simultaneously. When a navigator marks ocean routes, the map stays still. But in astronomy, half the distance required to define a parsec is gone the moment it is measured, because Earth has left that place. Nothing in the sky is held still long enough to be measured directly. Every measurement becomes an echo. The parsec forces an uncomfortable realization. The human attempt to assign fixed distance in a moving universe is an act of abstraction, not of physical truth. That realization eventually deepened into revolution. Because distance, as defined by parallax, implied that the cosmos was not fixed. It implied depth, immeasurable, vertiginous depth. The stars were not painted lights on a crystalline dome. They were islands separated by unfathomable stretches of emptiness. A single parsec is roughly 3.26 light-years. And a light-year is already nearly 10 trillion kilometers. Therefore, a single arcsecond shift, barely visible, almost impossible to see, meant staggering separation. This destroyed the ancient picture of a universe in reach. When Bessel measured the shift of 61 Cygni, the world learned that every star seen with the naked eye stood at distances beyond ordinary imagining. Even the nearest stars lay multiple light-years away. Most lay hundreds, thousands. Distance stopped being local. It became existential. Yet even now, the strange logic of the parsec holds. Earth is the ruler, but the ruler never sits still. Distance measured in motion remains an unsettling idea. To say that a star is 10 parsecs away means Earth's orbit would have to be repeated 10 times as a baseline, and its angular displacement multiplied accordingly. But Earth's orbit is not a line, nor is it fixed. It is a continuous arc through space, influenced by gravitational distortions, planetary tug, and solar drift. Even the baseline itself moves. The sun travels around the galaxy. The galaxy drifts relative to others. Space expands between galaxies. So the very reference used to define distance slowly dissolves into cosmic migration. Yet the elegance of the geometry remains. The parsec is nothing more than the geometry of sight. Not how far an object is. Not how large it is. Not how bright. Only how the universe shifts behind it, infinitesimally, almost imperceptibly, when Earth changes perspective. Astronomy could then translate the smallest visible tremor into meaning. 1 arcsecond. 1 baseline. 1 triangulation. A distance called a parsec. But understanding why this defies intuition requires stepping into deeper consequence. Because the parsec is the first step toward relativity. In the early 20th century, Albert Einstein entered the story. His ideas did not discard parallax. They validated the deeper implication beneath it, that distance is inseparable from motion. For Einstein, no measurement existed independently of its reference frame. A meter stretched along railroad tracks changed length for an observer moving near light speed. Time slowed in accelerated environments. Simultaneity dissolved across distances. If motion affects time, and time is woven into space, then distance, any distance, is contingent. The parsec had unknowingly foreshadowed this. Because measuring distance by the position Earth once occupied is already a relational definition. It states, without naming it, that space has no fixed stage. The universe is not measured from some external vantage point. There is no cosmic ruler, no grid printed across the galaxy. Measurement exists only within perspective. When Earth moves, that movement creates meaning. Einstein simply widened the lens. Suddenly distance itself could shift if motion changed. Light became the only constant. Everything else bent or stretched. Thus, the parsec lives at a philosophical crossroads. It is a measure that works only because Earth moves. Yet Earth's movement is not constant. Its orbit is not a circle, it is an ellipse. Its gravitational environment evolves. Its reference frame drifts. The universe becomes relational geometry, not rigid space. Every star measured through parallax becomes part of a vast collapsing lattice. Updated, corrected, recalculated, refined as satellites improve precision. Gaia, the space telescope that now maps distances, does not look outward alone. It monitors Earth's movement, frame by frame, correcting its own shifting vantage, sharpening every arcsecond into truth. And once again, distance is defined not by the star, but by the motion of the observer. There is a quiet consequence hidden within this. Distance in the universe does not exist until it is measured. Before measurement, a star holds no fixed number. Its separation is undefined. Distance is born only when perspective creates measurable distortion. Parallax is thus more than technique. It is the philosophical fracture point where humanity realized that reality is not absolute. Nothing sits still long enough to be measured independent of motion. Stars drift. Galaxies expand. Space stretches. The baseline evaporates. Yet within this movement, measurement becomes possible. A triangle drawn between a star and two shifting positions of Earth becomes the only stable truth across cosmic scale. A truth built from motion. A truth built from impermanence. And so the parsec does not make intuitive sense because intuition evolved on a world where distance is local, physical, tactile, something walked or measured by extending arms across known terrain. The stars ignore such rules. Their distances can only be known indirectly, through angles so small that early telescopes could not contain them. A universe measured through trembling displacement. A universe where perspective determines reality. Astronomy became the study of motion long before Einstein explained why motion defined space. Humanity learned that numbers describing distant suns were not properties of the stars at all. They were reflections of how far Earth must travel to detect their truth. A parsec is the echo of 6 months of motion. A fragment of Earth's orbit. A memory of location. An angle. A shift. A star measured not by what it is, but by how the universe changes behind it. And in that definition lies the first tear in the old concept of reality, a tear that would later widen into relativity and into the modern understanding of space itself. A distance defined not by existence, but by change. Across the quiet darkness of the night sky, the stars appear fixed, like ornaments suspended beyond change. But the deeper astronomy looks, the more reality reveals itself through angles so small that the human mind cannot easily picture them. Parallax became the first tool capable of extracting distance from nothing more than shifting perspective. Yet its mathematics would soon reveal something unsettling. The universe is measured not by what can be seen, but by what almost cannot. At first, the angles seem trivial. 1 arcsecond. Sometimes half. Sometimes less than a tenth. Modern observatories speak of precision down to microarcseconds, millionths of a degree. To understand such smallness requires stretching imagination beyond familiar scale. A single arcsecond is equivalent to the width of a human hair seen from tens of meters away. A microarcsecond shrinks that same width to thousands of kilometers. It becomes a trembling line inside emptiness. A deviation smaller than thought, smaller than movement itself. Astronomy becomes the measurement of invisibility. And yet, through this invisibility, distance emerges. Because parallax is governed by a single rule. The farther away something is, the smaller its apparent shift becomes. Distance does not widen clarity, it erases it. A nearby star shifts slightly when Earth moves. A farther star shifts less. A star hundreds of light years away moves so little that the movement dissolves into stillness. Here begins the strange mathematics of triangulated reality. Parallax defines distance through the collapse of angle. In the geometry of space, triangles do not grow, their measurable angles shrink. The triangle between Earth's two orbital positions and a distant star becomes increasingly thin, so thin that its apex nearly disappears. For distant stars, that apex becomes indistinguishable from zero. Mathematically, astronomers write the relationship simply. Distance is proportional to 1/parallax. One number goes down, the other rises. But this simplicity conceals philosophical shock. Because when distance grows large enough, when stars lie thousands of light years away, the angle becomes so small that it can no longer be detected. The triangle does not disappear, the universe does. Its measurable shape dissolves into perfect symmetry, where motion no longer changes what is seen. Distance becomes uncertainty. In ancient seasons, humanity feared such uncertainty. The sky seemed too distant to measure. The stars hid meaning behind unreachable scale. For centuries, astronomers attempted to detect stellar angle only to find no change at all. The mathematics explains why. The shift grows smaller than instrumentation. Reality moves beneath perception. In the early 19th century, micrometers allowed measurements to 1/100th of an arcsecond. It was enough. Bessel detected it. Humanity stepped into distance. But as telescopes grew sharper and detectors gained sensitivity, the stars pushed farther away. Their angles collapsed again. Small angle, large distance. Smaller angle, larger still. Eventually, even with instruments orbiting outside Earth's atmosphere, a star at great distance produces an angle indistinguishable from zero. Gaia, the satellite mapping more than 1 billion stars, is capable of measuring shifts as small as tens of microarcseconds. Yet beyond certain thresholds, even Gaia cannot separate motion from stillness. The universe hides behind geometry. The observer sees stasis not because stars do not move but because the triangulated angle has collapsed into invisibility. And from this collapse emerges something profound. The universe becomes unknowable through direct means. The farther humanity looks, the less it can see. Distance stops being measurable using parallax and must be inferred through other cosmic signals: brightness scaling, spectral shifts, standard candles, variable stars whose rhythmic pulsing reveals intrinsic luminosity. But parallax remains the only method rooted in direct observation, unmediated by assumptions of stellar nature. Geometry itself becomes uncertain at cosmic scale. If a star lies an infinite distance away, its parallax angle becomes exactly zero. The triangle collapses. Distance loses definition. Space becomes indistinguishable from nothing. Mathematically, this leads to a boundary that behaves like a horizon, a limit where triangulation cannot cross. Astronomy meets a barrier not of tools but of existence. The logic reveals itself starkly. Measure distance. By measuring the vanishing of measurable change. The more something resists change, the farther away it must be. The cosmos becomes inverted intuition. Here on Earth, things that seem larger are closer. In space, things that seem unchanging are farther. Motion becomes meaning. Each arcsecond measured is not a simple angle. It is an inverse distance locked behind an invisible displacement. The mathematics of triangulated reality does not describe stars alone. It describes perception. Because the universe does not shrink its distances for convenience. It hides them behind decreasing angles until the observable world runs out of measurable change. This leads to a deeper consequence. If a star shows no parallax, one of two things must be true. Either its distance is infinite, or finite yet beyond the limit of detection. Astronomy, therefore, cannot distinguish between the two through parallax alone. Cosmic uncertainty begins. Scientists turn to layers of inference: luminosity classes, absolute brightness, Cepheid variable pulsations, redshift, the Tully-Fisher relation, supernova decay curves. Each method builds a ladder upward, moving beyond the collapsing geometry. But triangulation remains foundational. The angle becomes the reference point for everything else. If a Cepheid variable lies too far away for measurable parallax, astronomers calibrate its brightness using stars nearer by triangulated distance. Redshift becomes meaningful only because nearby galaxies anchor the scale. Every cosmic yardstick inherits its truth from the smallest detectable angles. Invisible geometry shapes all other knowledge. And yet, there is another layer often overlooked. The shrinking parallax angle reveals something deeper about space itself. Because endless distance means the angle approaches zero, but never quite reaches it. Space becomes infinite not because its measure grows, but because its angle collapses toward perfection. The apex of the triangle flattens. Reality becomes asymptotic. No matter how far away an object lies, geometry continues. Only its visibility fails. In mathematics, infinite distance is not a plateau. It is a vanishing point. The stars stretch outward toward that vanishing point. The observable universe contains billions of galaxies, each a swirling disk of stars too distant for parallax. Their movement becomes stillness. Their distances become inference. Yet astronomers understand them through the same geometry that once measured a single star in Cygnus shifting by less than a fraction of a hair's width. A collapsed angle led to everything. There is an irony embedded here. The most fundamental structure of distance emerges not from certainty, but from its disappearance. Parallax measures the smallest deviation possible. That deviation decreases until it cannot be measured, and that decrease reveals scale beyond comprehension. The universe allows no larger triangle. It only shrinks the apex. Infinite distance becomes indistinguishable from infinite stillness. Astronomy remains tethered to that limit. Beyond certain boundaries, triangulation cannot proceed, and what lies farther must be built through chains of assumption. Observers face a horizon not of darkness, but of diminished angle. The deeper implication emerges slowly. Reality is triangulated, but only where motion affects sight. Everything farther dissolves. The cosmos becomes a gradient of knowable space fading into unmeasurable magnitude. The mathematics becomes philosophical. No observation in the universe can access all distance directly. Even the nearest galaxies refuse parallax clarity. Their angles are far below microarcsecond precision. Measurement becomes faith in physical law. Uncertainty becomes structure. And that uncertainty is not failure, it is definition. Because the universe is not built in scales approachable by eye. Distance scatters itself beyond the limits of geometry. The measurement collapses, and through that collapse, the cosmos declares its immensity. Astronomy, therefore, is not about observing what is visible. It is about interpreting what shifts, however slightly, what trembles behind stillness. The strange mathematics of triangulated reality reveals a universe that cannot be grasped directly. Its truth arrives through diminishing angle, the vanishing trace of motion. The cosmos recedes behind invisibility, and humanity measures it anyway. The Milky Way appears as a luminous stripe across the night sky, soft, diffuse, unbroken. To ancient eyes it seemed continuous, like the glow of distant smoke drifting across darkness. But the modern map of this galaxy was not drawn by looking outward. It emerged from the mathematics of angles so small they nearly vanish. Because every measure of galactic structure began with an invisible shift, a tremor of position, a displacement smaller than a mote of dust drifting across a mirror. The parallax of nearby stars became the first rung in a ladder that would stretch across the galaxy and into its spiraling arms. Those motions, fractions of arcseconds, became the coordinates from which everything else unfolded. Parallax distances revealed a truth that could not be seen by eye. Stars are not evenly scattered. They lie in gradients, clusters, arcs of formation, and streams of gravitational inheritance. From these distances, astronomers began assembling the structure of the local stellar neighborhood. The nearest 1,000 stars were positioned. Their luminosities were compared. Their temperatures placed onto diagrams. And slowly, reality resolved into pattern. The first step in building the Milky Way was not looking outward. It was defining the distances within reach. Through parallax came the distances of the closest stars. From those stars came luminosity references. From those luminosities came the ability to measure farther stars. The universe revealed itself outward, step by geometric step. This became known as the cosmic distance ladder, a structure translated not through intuition, but calibration. Parallax formed the base. Every other method leaned on its precision. If nearby stars measured by parallax emitted a known brightness, then farther stars with the same characteristic glow must be farther away. This inference became the mechanism for measuring beyond where angles collapsed into invisibility. The geometry became inherited truth. Spectral fingerprints became markers. Brightness became distance. Luminosity became scale. Here, Henry Norris Russell, Ejner Hertzsprung, and others created diagrams placing stars into relationships. Temperature versus brightness, mass versus lifetime. The main sequence emerged, an evolutionary river on which stars drift depending on age and size. But its scale could only exist because parallax distances anchored its axis. Where no angle could be seen, luminosity spoke. A blue-white star shining as brightly as one measured through parallax must lie farther away. A faint red dwarf of matching type must be closer. Thus light became distance. And once distance became light, the Milky Way could expand. Astronomers extended outward through Cepheid variables, stars whose brightness oscillates with precise rhythm. Their periods became galactic metronomes. Their pulses conveyed truth. Within each pulse lay luminosity. Within each luminosity lay distance. Within each distance lay position in the galaxy. Cepheids were cosmic lanterns. Their peaks revealed spacings across thousands of light years. Their rhythms became markers of longitude and depth within the spiral arms, bridging the gap between parallax and the unseen edge of the galaxy. Through them, astronomers realized something surprising. The Milky Way was not a local scattering of stars. It was a system of structure. Long arcs extended outward. Dark voids separated dense star-forming regions. Dust clouds swallowed light. The galaxy became architecture. Mapping these regions required distance upon distance, each layer built on the one beneath it. Because nothing in the sky could be measured directly. The spiral structure was invisible from Earth. Clouds of dust washed across the galactic plane. Stars vanished behind curtains of absorption. What appeared continuous was, in truth, fragmented. Yet mathematics connected the fragments. The nearest stars measured by parallax created luminosity anchors. Those anchors defined the properties of distant Cepheids. Those Cepheids revealed long-distance structure. And behind those distances, entire spiral arms emerged. This chain of reasoning revealed something extraordinary. Every map of the Milky Way, every spiral diagram, every scale estimate, exists because one star, once, shifted slightly against the sky. From that shift emerged parsecs. From parsecs emerged light. From light emerged structure. Astronomers built models of stellar distribution. Radio telescopes traced hydrogen clouds through Doppler shift. Infrared systems pierced dust. Observatories began locating star-forming regions. But each new method layered itself on inherited truth. The parallax of nearby stars became the calibration of everything larger. Even today, cosmic cartography exists by extrapolation from that first geometric principle, Earth, 6 months apart, forming a baseline of 300 million kilometers across which the sky shifted by angles barely measurable. The Milky Way was not drawn visually. It was triangulated. Through dust. Through distance. Through motion. The galaxy never appeared as a spiral to human eyes. Even through a telescope, no sweeping view reveals its structure. Its shape was discovered through mathematics. Parsecs became the invisible grid beneath every cosmic map. The nearest clusters confirmed themselves through direct parallax measurement. Their brightness became reference. Their stars populated the main sequence. Their variables pulsed in calibrated rhythm. The ladder stood, and through it, scale emerged. For the first time, astronomers placed Earth not at the rim of something small, but deep within a rotating disk containing more than 100 billion suns. Though these values changed over decades, estimates shrinking or stretching as data refined, the underlying reasoning remained constant. Parsecs turned position into structure. Galactic radius, derived from stellar calibrations. Rotation period, derived from measurable velocities at known distances. Mass estimates, expressed through the distribution of stars compared against gravitational pull. Everything became relational. The Milky Way was built from relationships between brightness and angle, between luminosity and distance, between rhythm and scale. Today, Gaia adds a deeper tier to the latter. With precision approaching tens of microarcsecons, more than 1 billion stars now sit on a map defined not by lines or photographs, but by mathematical inheritance. Clusters appear as debris trails. Streams emerge from ancient collisions. The galactic disk ripples like frozen waves of gravitational memory. But even now, the map is still not direct sight. It is reconstruction. Coordinates stand in place of vision. And this leads to the quiet truth of this chapter. Our galaxy is known entirely through inferential geometry. The spiral arms exist because distances map outward from parallax measurements. The scale exists because brightness aligns to geometric calibration. The thickness of the disk exists because clusters separate by measurable distance. Stars do not appear arranged in structure. Structure emerges when distances reveal patterns. The Milky Way was not seen. It was solved. Every curve of its spiral, every estimate of its diameter, every assumption of mass, all originate from one invisible angle first detected in a star that moved almost imperceptibly. A shift of less than a hair's width across impossible darkness became the cornerstone of galactic truth. The Milky Way stands today not as a seen shape, but as a mathematical revelation, a structure constructed from parallax dust, a galaxy measured through diminishing angles, a cosmic home discovered not by looking outward, but by mapping inward first. And through that collapse of angle, humanity learned something profound. The universe cannot be witnessed directly. It must be decoded, one invisible displacement at a time. Across the dark sky, every measurement stands beneath the weight of imperfection. Nothing observed from Earth arrives untouched. Nothing that enters a telescope remains pure. And every distance in the universe is bent, minutely, invisibly, by the trembling nature of the planet beneath those instruments. For more than a century, astronomers tried to measure the geometry of the stars by drawing triangles against the sky. But the triangle was never still. Its vertices shifted, drifted, blurred. A distance measured tonight would never be identical a decade later. And every parsec, the quiet unit sitting beneath cosmic mapping, carried a shadow of uncertainty. Atmospheric distortion. Light falls from space perfectly straight. But as it descends toward Earth, the atmosphere wrinkles it. Air currents rise and collapse. Temperature gradients bend photons sideways. Even calm sky ripples like heated glass. A star that should sit still flickers. Its position oscillates. Not visibly, but microscopically. To human eyes, the star twinkles. To mathematics, the star wanders. This is atmospheric turbulence, measured in fractions of arcseconds, yet large enough to corrupt precision. Before the age of space telescopes, no observation escaped it. Every measured parallax angle passed through an ocean of moving air. Even the ancient observatories noticed inconsistencies, though only modern optics revealed the true cause. A star's geometric truth was blurred before it ever reached the instrument designed to capture it. Instruments shaking. No telescope stands perfectly still. Steel contracts. Foundations shift. Wind vibrates structures built toward the sky. Even the best observatories move, by millimeters, sometimes less. But when a measurement is taken in microarcsecons, a subtended angle so small it must be expressed in millionths, the smallest tremor becomes seismic. A momentary vibration becomes a new false position for a distant star. A misaligned mirror shifts a star's apparent coordinate. A tracking motor introduces microscopic lag. Errors hide in fractions of motion. And in astronomy, those fractions become distances measured in thousands of light years. The star has not moved. Earth wobbling. The planet itself does not hold its coordinates steady. It drifts like a ship at cosmic scale. Earth wobbles through a motion called polar wandering. Its axis precesses, a slow circular sweep lasting roughly 26,000 years. Its crust flexes under tides raised by the moon. Its rotation rate fluctuates under seasonal redistribution of mass. Satellites compensate for it today. Mathematical tables correct it. Atomic clocks track the shifting seconds. Yet the geometry still changes. A triangle drawn today, measured between Earth's orbital positions 6 months apart, is not the same triangle measured decades later. Its baseline, the diameter of Earth's orbit, changes length by centimeters each year. Its orbital eccentricity drifts. Its tilt shifts against the background of stars. The foundation for parallax geometry never stands still. Stars in motion. For centuries, astronomers assumed the heavens stayed fixed. Only Earth moved. But then proper motion was detected. A star does not remain where trigonometry leaves it. It travels, slowly, invisibly across the sky. Barnard's star moves fastest, covering the width of the moon in only a few centuries. Alpha Centauri shifts perceptibly over a human lifetime. Tens of thousands of stars drift over time scales smaller than cosmology. The triangle used to measure distance dissolves with motion. What was once a clean system, 3 points forming a measurable angle, becomes unstable. Point A moves. Point B shakes. Point C is not fixed. It is geometry against moving targets. The star seen today is not where historical tables placed it. A star initially measured at 4.2 light-years becomes 4.3 when recalibration arrives generations later. The slippery nature of celestial motion built uncertainty into the distance ladder itself. Technology begins to correct the instability. Human error is not corrected by intuition. It is replaced by engineering. Michelson interferometry changed the path. Instead of pointing a telescope at a star, interferometers combine multiple telescopes into one conceptual lens. 2 separate mirrors absorb a wavefront. Their incoming light interferes. Patterns emerge, minuscule, mathematical fringes. The fringes reveal distance. Not by brightness. Not by twinkle. But by the wave structure itself. Michelson interferometry reduced shaking into measurable phase offsets. Where traditional telescopes blurred, interferometers sharpened. An observatory became not a window, but a ruler. It measured wavelength, spacing, interference, drift. The star no longer needed to sit still. Its light encoded information in oscillations. Adaptive optics remakes starlight. Then came the moment when atmospheric distortion became soluble. Adaptive optics did something profound. It reshaped light after the sky had damaged it. A reference beacon, often an artificial laser star, was projected into the atmosphere. Sensors observed how turbulence warped that artificial point. Mirrors flexed in real time, hundreds of times per second, changing curvature to reverse distortion. A new image emerged. Stars sharpened. Angles stabilized. Positions refined. Distances that once fluctuated began to converge. An arcsecond could become a microarcsecond. A microarcsecond became reliable. The triangle regained clarity. Ground distortion modeling. Even the solidity of Earth entered the calculations. Continents move. The crust shifts. Tectonic drift inches observatories across the planet. Modern measurements incorporate GPS-level Earth modeling so precise that placement errors shrink to millimeters. And from those millimeters, parallax angles emerge, unchanged, unmoved. Earth's breathing becomes mathematically subtracted. The planet shakes, bends, rotates, tilts. But its motion is now known, stored, and removed. Only the star remains. Cosmic truth through correction. But there is an unspoken irony. Every error removed reveals a deeper difficulty. When uncertainty shrinks, the observable horizon expands. Distances once unmeasurable become measurable. Then distances beyond those become uncertain again. With each improvement, astronomy enters greater fragility. A microarcsecond of uncertainty at the limit of Gaia's measurements corresponds to tens of thousands of kilometers of error across space. Technology sharpens truth. But naked truth exposes more unknowns. The farther the target, the smaller the angle. Until the angle collapses into noise. Even at its peak precision, the cosmos hides behind distance. A measurement against fading geometry. A parsec is defined by parallax. Parallax is defined by angle. Angle is defined by distance. But distance recedes faster than measurement improves. Galaxies drift farther away with cosmic expansion. Stars migrate under gravitational tides. The very geometry of space-time stretches. Thus, a mathematical paradox forms. If precision increases slower than distance expands, the universe grows more uncertain over time. Even with perfect instruments, stars move. Even with Earth stabilized, light bends around dust. Even with distortion removed, cosmic acceleration increases separation. The triangle never stays fixed. The invisible shadow inside every measurement. Every cosmic distance written in scientific literature includes uncertainty bars. Some are wide. Some are microscopic. None are zero. A parsec is the cleanest number astronomy can produce. Yet even it is wrapped in uncertainty. Not because the universe is inconsistent, but because reality sits beyond the resolution of instruments built from shaking metal on a spinning world. And so every galaxy map, every stellar catalog, every cosmological chart carries this quiet truth. Distances are not revealed. They are reconstructed. They are interpreted through noise, correction, probability, compensation, and time. At the limits of measurement, a concept emerges. The observable universe might be precise enough to chart, but not precise enough to hold still. It moves faster than certainty. And so humanity's greatest clarity about space is not mathematical perfection, but confidence wrapped around uncertainty. Not truth in isolation, but truth corrected over decades of motion. A parsec remains the anchor point of stellar geometry, a thread between light and distance. Yet inside it lives error, measured, modeled, minimized, but never eliminated. The universe is mapped through disappearing angles, and shifting foundations, and fading lines drawn between moving stars. And the human effort to measure across the darkness continues against that quiet instability, rewriting the cosmos, one corrected triangle at a time. There is a distance at which geometry stops working. Beyond it, the sky offers no movement, no shift, no measurable angle. And the method that once defined cosmic truth begins to dissolve. For centuries, astronomers believed that everything could eventually be measured through parallax, if only instruments became sharp enough. But distance expands faster than precision. And the further the stars recede, the smaller their angles fall, until those angles collapse into invisibility. At 1,000 parsecs, the displacement of a star over 6 months becomes smaller than the width of a hydrogen atom seen at arm's length. Beyond that, the displacement disappears completely. The universe becomes still, so still that measurement breaks. And in that stillness, astronomy is forced to move away from geometry, into inference, into theory, into something both abstract and uncomfortable, where angles collapse into silence. Parallax is built on differences, two positions of Earth, separated by half an orbit, forming the baseline of a cosmic triangle. Distance emerges from that triangle. But triangles require angles. And angles require movement. When measurement can no longer detect movement, distance collapses into assumption. A star might sit 10,000 parsecs away. Or 20. Or 50. The sky does not change enough to distinguish. At that scale, the universe becomes smooth, featureless in motion, like a painting set on glass. From that still surface, astronomers face a philosophical break. The cosmos exists beyond the reach of geometry. Space becomes too large for direct observation, and science turns to methods that are not based on seeing, but on interpreting. Hubble begins to suspect expansion. In 1910, parallax ruled the universe. Stars were points that shifted. Distance could be drawn through measurable change. But as telescopes pushed farther, they discovered something unsettling. Millions of stars did not move at all. Nebulae drifted across photographic plates, not sideways, but spectrally. Their light stretched. Not physically stretched, spatially stretched. The wavelengths elongated. They reddened. The farther an object sat, the deeper its spectral lines shifted. Edwin Hubble turned that shift into measurement. He plotted galaxies, distance against velocity. The relationship formed a slope. The slope revealed recession. Not orbit. Not motion around the Milky Way. Motion away from everything. The universe was not stable. It was unfolding. Galaxies fled one another as if space were stretching beneath them. The geometry of parallax was useless here, because objects moving away did not shift against the sky. Motion existed not in position but in wavelength. Distance was now tied to redshift. A new ladder replaced the triangle. But the triangle remained broken, insufficient, yet still foundational. Einstein rejects the static universe. Theory resisted the data at first. Einstein initially favored equilibrium. For mathematics to balance, the universe must remain fixed. Even gravity, in his early formulation, demanded stability. Cosmic expansion shattered that assumption. When he saw Hubble's graph, he conceded what the geometry implied. Space itself was stretching. Metrics of distance could no longer rely on simple angles. A baseline drawn today became a different baseline a million years later, because even the baseline was expanding. Every astronomical shape elongated. Every triangle widened. Not because the universe moved outward from a center, but because every region of space pushed away from every other region. Distance was not motion measured through position, but motion embedded into the structure of spacetime. Parallax had met its horizon. Geometry had lost its authority. The universe was not static, therefore a static method could no longer reveal it. When parallax vanished, astronomy fractured. At large scales, angles became illusions. The distances printed in tables became estimates. Measured truths became theoretical projections. Astronomy entered a silent divide. One world measured. The nearby stars, the local neighborhood, the region that still exhibited movement. One world interpreted. The stars too far to shift, the galaxies that never changed position. Local truth was precise. Cosmic truth became uncertain. Distances derived from parallax remained sacred, but those distances stopped early. Beyond that invisible threshold, the universe blurred. Astronomy stepped into the unknown. Redshift replaces geometry. Where geometry failed, light filled the space. A spectral line shifts toward red. The shift correlates with recessional velocity. Velocity correlates with cosmic distance. A galaxy too far for parallax becomes measurable through wavelength, leading to a paradox. Motion reveals distance better than angle. A star does not need to move to reveal its position. It only needs to stretch its light. Thus, the cosmic ladder rewrote itself. Parallax at the base. Spectral fitting above it. Standard candles above that. Redshift scaling above that. A hierarchy built upon collapsing measurement. Distance became a chain of inference, where error magnified with every link. Yet no alternative existed. The universe demanded interpretation. And interpretation required surrendering geometric assurance. Parsec dethroned, not erased. The parsec was defined by parallax. It represented clarity. 1 arcsecond at 1 astronomical unit. A triangle so elegant that distance had once felt measurable and finite. But the universe is neither finite nor measurable beyond its own horizon. The parsec was dethroned, not discarded, not replaced, but widened into irrelevance at cosmic scale. It remained foundational only to a limited sphere. Within a few thousand light years, it maps truth. Beyond that, uncertainty expands faster than precision. Yet even dethroned, the parsec remains the first rung of the ladder. Everything above still depends on what sits beneath. Cosmic distances require Cepheids. Cepheids require calibration. Calibration requires parallax. So even when parallax breaks, everything above it still stands upon its broken remnants. Science learns to use failure as foundation. Astronomy learns something profound. A broken measurement framework is still a framework. A limited truth is still truth. Parallax never vanished. It simply shrank into the bottom of a structure far taller than geometry. Its collapse revealed what was beyond it. When stars no longer move, other signals must. Light changes shape. Brightness oscillates. Time evolves through cycles. Galaxies speed away. Measurement changes language, but reality remains intact. Science moved from rulers to waveforms, from angles to velocities, from triangulation to expansion. Not because parallax failed, but because it succeeded until it reached the wall of infinity. At that wall, the visual universe became silent. Then the spectral universe began to speak. The narrator reflects. A quiet irony remains. Every model of the expanding universe, every distance of every galaxy, every metric of cosmic scale, is built upon distances measured from shifting points so small that Earth's atmosphere could erase them. Humanity used something nearly imperceptible to measure something immeasurable. A collapsing method became the seed of infinite measurement. A disappearing angle became the foundation of expansion. The universe is charted by watching what no longer moves. In its stillness, motion emerges. In its silence, expansion is heard. In geometry that fails, cosmology begins. There is philosophical humility in that realization. Science is not a ladder that climbs with certainty. It is a ladder built from unstable rungs, each supporting the next, each bending under weight, each revealing a level above itself. Parallax broke, not dramatically, not suddenly, but quietly, mathematically. It faded beyond usefulness. It surrendered. Yet, in that surrender, the universe opened. Distances became wavelengths. Motion became geography. Expansion became structure. And the cosmos, measured through a broken instrument, became infinite. The small movement of nearby stars shaped the understanding of galaxies rushing away at thousands of kilometers per second. The smallest measurement in astronomy revealed the largest phenomenon ever discovered. Through failure, the universe became measurable. Through vanishing angles, infinity unfolded. There are instruments that merely observe the universe, and there are instruments that rewrite it. The European Space Agency's Gaia telescope belongs to the second category. Launched into orbit around the L2 gravitational point, Gaia began its mission not by looking outward into deep space, but by turning inward toward the Milky Way itself. Its purpose was simple in description, impossible in execution. Measure the positions and motions of stars with microarcsecond precision. An angle so small that a single arcsecond would need to be divided 1,000,000 times to reach it. An angle smaller than imagining the shifting of a snowflake on the surface of the moon. Gaia did not map the sky. It measured motion so faint that the concept of movement itself had to be redefined. The result was not a star catalog. It was a cinematic reconstruction of the galaxy in motion. A three-dimensional Milky Way. Living, shifting, twisting. And like all revelations at cosmic scale, it did not just clarify. It broke things. It rewrote distances believed to be correct for generations. It dissolved assumptions that had once steadied astronomical thinking. It reshaped the geometry of galactic structure. The map of the galaxy, once believed elegant, became unstable. Gaia measured not the present sky, but the sky unfolding. Previous stellar catalogs were static. Names, positions, brightness. Gaia's scanning system turned those still images into kinetic forms. The satellite observed the sky continuously, allowing proper motion to be measured for billions of stars. Tiny drifts, slow slides, shearings of stellar patterns across time. Very few stars are fixed. Almost none move along neat circular paths. The Milky Way, once imagined as a grand wheel of stars rotating uniformly, revealed itself instead as a turbulent migration field. Stars slip inward toward the galactic core. Others drift outward toward the edges. Some shoot above the galactic plane like sparks from a grindstone. Others fall beneath it, following trajectories inherited from ancient gravitational encounters. The galaxy is not a structure of balance. It is a structure of motion. Gaia's parallax shattered astronomical certainty. Before Gaia, Stellar distance was an architecture built on approximation. There were precise measurements near Earth. But beyond a few hundred parsecs, uncertainty multiplied. Gaia did not eliminate uncertainty. It exposed where uncertainty had been accepted as knowledge. Distances once printed confidently became obsolete. Entire catalogs were rewritten. Not slightly adjusted. Rewritten. A star believed to sit 900 light-years away suddenly moved to 1,300. Clusters believed to be gravitational siblings turned out to be strangers. Stellar groups once treated as coherent families revealed fractures, members moving apart rather than together. The error was not intentional. It was rooted in instruments that could not see finely enough to discern reality. Gaia did not fix the past. It revealed that the past had been mathematically constructed. Parallax curvature, a map with depth. Gaia did not draw a flat image of the Milky Way. It extracted curvature. In traditional atlases, parallax was expressed as linear shift. Gaia expressed it as geometric field. Each star carried not a single data point, but a set, position, distance, motion along the sky, motion toward or away, brightness parameters, temperature estimates, spectral classifications. The results were layered. A topographic-like density field, a velocity gradient map, a distribution of star ages across the galactic disk, patterns of migration. It revealed the Milky Way as an ecosystem with flow. Not static, not fixed, but hydrographic in structure, like currents in an ocean. Stars do not orbit so much as circulate. They shear against the gravitational tide of the galactic bar. They oscillate vertically, rising above the disk, falling below it again, in periods stretching tens of millions of years. The galaxy's shape is not determined by stars staying still. It is shaped by stars leaving traces across time. What Gaia broke inside the heart of astronomy. For decades, astronomy imagined that spiral arms were long-lived structures, grand symmetrical pathways carved into starlight. Gaia showed that these arms are not fixed. They are wavefronts, patterns of density that shift as stars pass through them. Stars do not belong to the arms. They migrate through them. What looked solid became transient. What looked permanent became dynamic. Spiral arms ripple, stretch, segments fragment, submerge, some dissolve. The map of the Milky Way on school posters, two noble sweeping arms, was revealed to be artifact rather than truth. Gaia replaced those clean arcs with distributed clusters, loose strands, diluted formations. Astronomers discovered that the galaxy's structure resembles not a spiral drawn in ink, but a turbulence field. A cosmic weather pattern, stellar migration, a slow exodus across time. Before Gaia, the Milky Way was imagined as gravitationally neat, stars rotating predictably along shared tracks. But Gaia revealed differential flow. Stars born in one region slip away over millions of years. Clusters dissolve. Families disperse. Generational patterns scatter. It is a dispersal that resembles smoke rising from embers. Gaia tracked these migrations backward. By reversing trajectories, it reconstructed stellar origins. Stars once assumed to be unrelated were revealed to share ancient birthplaces. Siblings long separated drifted back into genealogical lines. Clusters believed stable for millions of years turned out to be dissolving rapidly. The Milky Way does not maintain its structure. It loses it. Entropy unfolds in slow spirals. Gaia produced motion maps, galactic choreography. Across billions of stars, a strange harmony emerged. Patterns in movement were found, not random, but coordinated. Kinematic waves ripple outward from the galactic bar. Shock fronts form at intersections of spiral patterns. Star streams stretch thousands of light-years long, not clusters, but migration corridors. One of the most remarkable was the discovery of large-scale vertical oscillation. The entire disk rises and falls as if flexing, like a ripple frozen across the stellar sea. Not chaotic noise, a coherent pattern, likely born from gravitational shocks, possibly collisions with dwarf galaxies. possibly oscillations induced by dark matter density layers. Gaia revealed the galaxy not as a static object, but as a resonating structure, a chord played across millions of stars, some moving inward, some outward, some lifting above the plane, their trajectories converging into an unseen mathematics. Where certainty was broken, science expanded. Gaia forced a confrontation. Astronomers had to abandon a comfortable belief that the Milky Way was largely understood. Instead, Gaia showed that understanding had been approximation, a structure drawn from insufficient resolution. Gaia's mission produced something rare, not answers, but instability. Old values collapsed. Models had to be rebuilt. Entire fields reconsidered their foundations. That breaking was not failure. It was progress. Science advances not by protecting certainty, but by exposing that certainty as incomplete. Gaia did exactly that. The galaxy became three-dimensional enough to trouble belief. In previous centuries, astronomy lived within flattened skies. Star fields arranged in projection. Depth was inferred, rarely measured. Gaia inverted that. Its data placed stars behind stars behind stars, revealing layers. The galaxy is not simply vast. It is stratified. Young stars cluster along dense spiral filaments. Older populations drift like embers into the halo. White dwarfs trace evaporated clusters. Motion becomes timeline. Distance becomes history. Where parallax once offered geometry, Gaia offered chronology. The Milky Way does not merely exist. It evolves. And so Gaia redefined the galaxy again. There is a profound irony in astronomy's history. Each new instrument reveals error in the instrument before it, and each error leads not to collapse, but expansion of knowledge. Gaia is not the end of measurement. It is the beginning of uncertainty again, because now astronomers can see the complexity of motion and must explain it, because now distances are more precise and must be reconciled, because now the structure of the Milky Way includes turbulence, and turbulence must be modeled. Knowledge deepened, then destabilized. Maps refined, then destabilized. Truth sharpened, then destabilized. The galaxy became real at a level that prevented it from being simple again. Gaia did not reveal clarity. It revealed living structure. It introduced precision so high that even reality looks unstable. And that instability is now the most accurate description of the Milky Way ever made. In the unfolding horizon of astronomy, measurement is no longer a simple act. It is an odyssey across space, a negotiation with the universe itself. The Parsec, born from the subtle shift of a star across a 6-month baseline, has always been relational, defined not by a fixed ruler, but by motion, by perspective, by the Earth tracing its orbit. And now, in the 21st century, humanity stands poised to redefine the very meaning of distance. The instruments of tomorrow are not limited by Earth's gravity, by atmospheric turbulence, or by the faintest tremor of a telescope. Quantum baseline telescopes promise to reach sensitivities unimaginable by classical means, linking photons across interplanetary distances. Arrays of space-based interferometers will act as a single, virtual lens, spanning millions of kilometers, mapping parallax at a scale that would have seemed absurd to Friedrich Bessel. Imagine triangulation between Earth and Mars, the solar system itself forming a moving baseline, each orbit a new ruler, each planet a vertex in a cosmic triangle. Distances will be measured not from a static point, but from motion itself. A solar system flowing through the galaxy, a triangle drawn across moving points in space. Here, the philosophical implications deepen. Distance is no longer a simple metric. It is not absolute. It is relational. The universe does not hand us a yardstick. It presents motion. Matter reveals itself through displacement, through subtle shifts, through the unfolding of geometry in time. And so the paradox of the Parsec returns, magnified. A single object, appearing fixed, measured only because Earth and its companions in the solar system move, reveals immeasurable depth. The triangle drawn upon the sky is ephemeral, defined at one moment, reshaped in the next. Distance is an echo of motion, a testament to perspective, a record of where we have been rather than where things intrinsically exist. The Milky Way, once imagined as a serene spiral, is instead a tapestry of motion, turbulence, and migration. Gaia revealed stars moving in streams, clusters dissolving, spiral arms shearing and folding like currents in a river. And yet, even in that motion, the Parsec persists, not as a simple number, but as a method to apprehend the otherwise ungraspable. Future measurement systems will extend this principle across the solar system, across the galaxy, perhaps even between neighboring star systems, making distance simultaneously more precise and more ephemeral. Through this lens, reality itself becomes relational. A star's location exists not in isolation, but as a position measured against another. The universe does not contain distance. Distance emerges only through the act of measurement. It is the conversation between observer and observed, a dialogue of motion and time. Quantum baseline arrays, free from atmospheric distortion, will detect parallax angles so minute they approach the very limits of what is physically detectable. Time becomes a ruler. Motion becomes the unit of measurement. The solar system's continuous journey through space transforms every observation into a dynamic calculation. A star's distance is defined as much by where Earth was yesterday as by where it is today, and where it will be next month, next year. The Parsec, once a simple geometric abstraction, now becomes an instrument of cosmic philosophy. It forces the recognition that what we call reality is constructed from relations rather than absolutes. Matter does not reside in a fixed grid. It exists only in the context of observation, in the shifting angles of light, in the passage of time. Space is not empty. It is a field of relational potential, a lattice of possibility, a network of positions defined by motion. Humanity floats in this river of measurement, tracing infinity with instruments that can barely see the edges. Each observation is a negotiation between the limits of technology and the immensity of the cosmos. The further we push, the smaller the measurable angles become, and the more abstract our conception of distance. Yet every tiny shift, every microarcsecond detected, extends our reach, expands our understanding, and deepens the paradox. In this, the final reflection emerges. We do not measure stars. We measure ourselves against them. We track our own movement through space and call that difference a distance. The Parsec exists only because Earth travels endlessly through the void, because we persist in observation, because the cosmos offers itself in motion rather than in static presence. A parsec is not a number. It is a story of Earth orbiting the Sun, a story of instruments refining angles smaller than the width of a human hair seen across kilometers, a story of the human mind attempting to contain infinity within the precision of geometry, a story of triangles drawn on a sky that has no edges, triangles that exist only while they are observed, triangles that reshape themselves as motion continues. And so, as the solar system drifts through the galaxy, as Gaia and its successors trace billions of stars, as quantum interferometers stretch their virtual baselines across interplanetary space, the paradox of the parsec endures. One object, appearing smaller than comprehension, reveals immeasurable depth. Distance is not a thing. It is a measurement. It is motion rendered into meaning. It is a conversation with the universe that stretches across light years. And in the end, humanity does not stand outside the cosmos. It exists within it, drawing triangles on a sky without edges, measuring infinity by the shift of nothing, and calling that distance a parsec. In the vastness of space, this is both our first step and our perpetual journey. To know, to measure, to witness, and in witnessing, to define our place in the moving, endless, relational fabric of reality itself.